Hello and welcome to the third topic, nuclear chemistry of Unit 3 from National 5 Chemistry. Before I start this topic, I would expect the students to have a good understanding of atomic structure and to know all about isotopes. They should also know how to write nuclide reactions. So if you have any doubts regarding any of these topics, you can go back to my previous lectures, get a good grasp of these topics, and then start this new lesson. Isotopes, as you all know, are elements having same atomic number but different mass numbers. Generally, most of the elements are said to have isotopes, most of which are unstable. The stability of an isotope depends on its neutron-proton ratio. This can also be said as the stability of the nucleus in an isotope depends on neutron-proton ratio because nucleus contains both the neutrons and the protons. So here you can see we have four isotopes of silicon. So let's complete this chart to see which isotope is most stable and which one of them is least stable. Remember that the neutron-proton ratio should be either equal to 1 or very close to 1 for the isotope to be stable. So for all the isotopes of silicon, the number of protons and electron will be the same, and that would be equal to 14. If we look at the number of neutrons now, so the number of neutrons in the first would be 14, which is 28 take away 14, and the second one would be 11, 25 take away 14, and third would be 17, 31 take away 14, and the fourth would be 13. So the first one is having neutron proton ratio equal to 1, so this would be said to be most stable. And the one with the maximum difference of 17 and 14, which is this is the one which has got the maximum difference between the number of protons and neutrons, so this would be least stable of all the isotopes. Now, radioactivity. What is radioactivity? It is a phenomenon in which unstable nuclei changes to a stable nuclei by emitting a radiation and release of lots of energy. Now, these radiations can be of three kinds. They can be alpha particles, which is, as you can say, they are slow moving, positively charged particles which have bent towards the negative plate. Beta particles are fast moving, negatively charged particles which have bent towards the positive plate. Gamma radiations are electromagnetic radiations that have no mass and carry no charge, and they pass through the electric field undeflected. They are not affected either by electric or by magnetic field. So now looking at the properties of these three particles, alpha particle is a positively charged helium ion. So if we look at the helium atom, we know that helium atom has atomic number 2 and mass number 4. So if it is positively charged, take away both the electrons. So this would be helium atom having a charge of +2. And beta particle is a negatively charged electron. Gamma radiations have got no charge at all. Now, if you look at the charge of alpha particle, it's, we know, positively charged particle, and the charges is +2 positive. Beta particle is -1 negative. Gamma, no charge. Mass of alpha particle would be equivalent to mass of helium atom, which is 4, approximately you would say 4 atomic mass units, and that of beta particle would be equivalent to mass of an electron, which is 1/1837 atomic mass units, which is very, very negligible. And gamma rays have no charge at all. The penetrating power of alpha particle is the least, and it can be easily stopped even by a paper. Beta particles have got a greater penetrating power as compared to alpha particle, and they can be stopped by, say, a few millimeters of aluminium foil. Gamma particles have got the highest penetrating power, and they can be only stopped by few centimeters of lead sheet or few meters of concrete. Ionizing power of alpha particle is greatest, and that of gamma particles is the least. Electric field, as we know that alpha particles are positively charged particles, and being slow moving particle, they are slightly deviated towards the negative plate. Beta particles are very light particles, so they are greatly deviated towards the positive plate. Gamma particles are not deviated at all. Now, radioactive emissions or radiations take place from an unstable nuclei and change it to a stable nuclei. So, this emission of radiation from an atom generally changes its nature, except in the case of gamma radiations. You have to remember that small nuclei generally prefer a neutron proton ratio of 1. And unstable nuclei usually have too many neutrons. So, in order to gain stability, these unstable nuclei will have tendency to lose their neutrons, which breaks up into a proton and an electron. This electron is emitted as a negatively charged beta particle. So, the general equation for neutron emission would be that one neutron gives away, when it is given away, it breaks up into one proton having mass number and atomic number of 1 and one electron. So if you look at the example of silicon, you'll see that silicon, when it emits a beta radiation or a beta particle, it will change into phosphorus releasing one electron. Carbon, when it emits a beta particle, will change into nitrogen and an electron or beta particle is emitted. If you look at the equations again very carefully, you will see that whenever beta emission takes place from an element, it generally changes into another element that is subsequent to it in the periodic table. So silicon has atomic number of 14, phosphorus, which is produced as a result of beta decay of silicon, has atomic number 15. Carbon has atomic number 6, and nitrogen, which is the product of radioactive decay of carbon, has atomic number of 7. Isotopes that emit radiation are generally known as radioisotopes. So we know that smaller nuclei prefer a neutron proton ratio of 1, but large nuclei, they generally prefer a neutron proton ratio of 1.5 because they need more neutrons to support them. But even in large nuclei, unstable nuclei have got too much of mass. So generally alpha emission takes place. Alpha emission tends to reduce the mass and also improves the neutron proton ratio. So the general equation for alpha emission is that when alpha emission takes place from any element, the mass number of the element reduces by 4 and its atomic number reduces by 2. And an alpha particle with mass number 4 and atomic number 2 is released. So if you look at uranium atom, this, when emits an alpha radiation, changes into thorium, which has atomic number 90, 2 less than that of uranium, and mass number of 229, which is 4 less than that of uranium. Thorium again undergoes alpha emission, changing into radium, which has atomic number 88, again 2 less than thorium, and mass number of 225, 4 less than thorium. You have to remember that above atomic number 83 in the periodic table, almost all the isotopes are unstable. And these unstable isotopes, they have a tendency to undergo decay and even under natural circumstances, irrespective of physical or chemical conditions. So nuclear equations, they always show you the product of nuclear decay. And the way you balance the normal chemical equations in case of nuclear equations, you have to just balance the atomic number and the mass number on the reactant and the product side. So the sum of atomic number and the sum of mass number on each side of the equation should balance. So here is an example of carbon undergoing beta emission, changing into nitrogen and releasing a beta emission. So you can see that mass number on the top is balanced, as well as atomic number, and at the bottom as a subscript is also balanced. So let's give a go with this equation, that is iodine 131, which is used to study the health of thyroid gland. And when it undergoes beta emission, what would it form? So you can take the help from your data booklet, and you'll see that this, when it undergoes emission, it changes into xenon, releasing one beta particle. So your equation is all balanced. So there are a few more equations for you to practice, and you can pause the video here, practice these equations, and come back to check your answers. So let's do these equations. Polonium will change into astatine, and this will have atomic number of 85. So next equation is nitrogen. It gets one neutron, and this would change into carbon. So this will have argon, releases one beta particle, changes into chlorine, and you can see there are two isotopes of hydrogen. When they combine together, they would give you helium and releasing one neutron. This is an example of nuclear fusion, which we will discuss a little while back now, from now. Now, the last equation here you can see is one neutron being added to uranium. So this would be, and this undergoes nuclear fission, which means breaking down into smaller nuclei. So it forms strontium, and this would be 3894. So that is what it will form. I'm sorry, it would be serene. Yes. So this is the end of this lesson, and before I proceed to the next part of this same topic, uh, now nuclear fission and fusion. In nuclear fission, the nuclei of uranium or plutonium, which have atomic number greater than 83, break up into two smaller, lighter nuclei which are much more stable with the release of large amount of energy. So you can see here two equations, and in both the equations nuclear fission is taking place. So for the nuclear fission to start, neutron should hit the nucleus, which is any nucleus, maybe of uranium or plutonium. They form an intermediate nuclei which is very unstable, and then that breaks up. In case of uranium, it breaks into barium and krypton, releasing three neutrons. In case of plutonium, it forms xenon and zirconium, releasing again three neutrons. These three neutrons can further attack on three uranium particles, and here these three neutrons can attack three elements three atoms of plutonium. And so this reaction goes on endlessly, releasing large amount of energy. Nuclear fusion, on the other hand, is the reverse of nuclear fission. In this, two light nuclei, they are fused together to produce a heavy nucleus. So two isotopes of hydrogen, which is deuterium and tritium, they combine together to form helium, releasing one neutron and large amount of energy. This reaction takes place in the center of stars where the temperature and pressure is very high. And so you know that the optimum condition for nuclear fusion to take place is that it requires very high temperature and pressure to start the reaction. As I told you that these radioisotopes have a tendency to emit radiations and decay by itself, and that is a natural process. It is a random event that is independent of any physical or chemical conditions, and it continues endlessly. So half life is the term which is used to denote the time taken for the radioisotopes activity to fall to half. So this is generally measured in counters per minute, in and it could also be measured in time taken for a certain given amount of radioisotope to reduce to half. So if you look at a sample of a radioisotope here in the graph, so you can see that the initial mass of the sample is 100 grams and counts per minute is 250. So the time taken for it to reduce to 50 is 7 minutes. And this is the time when you can see that the counts goes down to 125 counts per minute. So as the activity reduces, the number of counts per minute also reduce simultaneously. Now we have few questions in this. So first is, a sample of a radioisotope has a half-life of 14 days. After 56 days, what mass of the original 80-gram sample remained? So a sample of 80 grams has a half-life of 14 days. And we are now looking at it after 56 days. So 56 days is 14 times 4, which means that the substance undergoes 4 half-lives. So the amount remaining would be, is always written as 1 half-life is half-life of this. So this raised to the power n would give you the amount remaining after n half-life. So here n is equal to 4. So this would be 1/16 of original mass, and this would be equal to 1/16 of 80 grams. So 5 grams would remain after 56 days. The next question is, you can see a graph here which shows the mass of iodine 131 in a sample, which changes over a period of time. So initially we start with 100 picograms, and we have to look at the time taken for the mass to reduce to 50 picograms, and this would be 8 days. So half-life would be 8 days. A radioisotope of carbon had an initial radiation reading of 200 counts per minute. 24 days later, the reading was found to be 50 counts per minute. How many half-lives occurred in 24 days? So the initial radiation is 200 counts per minute. So the half life would be equal to, which is 100 counts per minute. And 50 counts would mean one more half life. So it will mean two half life. So which means that in 24 days, it underwent two half life. Now let's look at the uses of radioisotopes. Radioisotopes of elements, they have wide variety of uses. Cobalt 60, it is a powerful gamma emitter which is used to treat deep-seated tumors, so it has a medical use. Iodine 133 also has a medical use because it is used to test the health of thyroid gland. Carbon 14 is generally used to date the fossils and look at the age of the fossil by looking at how much carbon content is remaining, because remember that most of our body is made up of carbon. Phosphorus 32 is a weak beta emitter which can be applied directly to treat skin cancer. Iridium 192 is used to detect cracks in jet turbines. Oxygen 18 is used to determine the mechanism of esterification reaction. I hope you remember the esterification reaction from Unit 2. If you don't, then you can go back to those lectures and just try and understand this term. So, this is the end of my topic. Hope you enjoyed the lesson, and again, see you in the next topic. Bye.